Cloud. Okay. Yeah. So, as I said, we are going to go through what it is that the examples we did. No examples. The work I gave you guys, exercise. So the first week that we're given is sorry, the first question was under the finding the domain function. So let me look for someone who actually solved down for the domain function. Let's see. Domain function. Nope. Let's get the limits. Okay, so I found someone who did the domain function. Who's this? I don't know. The person has got no name. Yeah, anyway, yes. So like I said, and the first question was gx is equals to the square root of x squared plus x, say plus x plus 2, and then the denominator was the same thing but then with negative sign. As I said, just as usual, the first thing you're supposed to do is you are supposed to equate the denominator to 0. So you say it's not equals to 0, and then from there, since in this case here we're given quadratic function, so in this case here, for you to find the values of x, you have to use the equation which was used here, which was used in that scenario, in that case. And then once you do that, you're going to find two values of x. You find one that's positive and one that's negative. Yeah. So those two that you're going to find are going to actually help you find what your domain function is in the first place. Yeah. So, where is that? Where are my papers? Okay, they're here. Okay. So, I'm sure the first x that was found, should have been 2. The other one should be -1. Yeah. Should have been 2 and should have been -1. Yeah. I'm not mistaken. Let's solve this one. Yeah. Let me see. Okay. So you found the value of x. You use the denominator to find the value of x. Let's see. That there you found square root of. So you found 3. You found the first one. Found the delta was equals to 3. Then 3 plus b. There I gave you 1 plus that there. Well, yes, yeah. So you found 1 and you found 2, which is perfect. So that's actually very correct. Because you found 2 and you found because you found 2 there. And you found 1, which is very much correct. Yeah. And then from there you have your 2, then you have your 1. But then what happened is that what happened is here you didn't draw the table. You're supposed to draw the table 2 here. The table here should have been drawn.
No. Can you kindly be sharing the things that you're talking about? Like.
Oh, okay. Yeah. Okay. Give me a second. Oh gosh. That's true. Hold on. I'm opening my DM right now. What number is this? 59 at the end. That's true. I'm looking for this same person's contact. This is the one. Okay. I'll just pick at random. I'll pick whoever who it is. Let me see. Okay, yeah. So this person did actually solve this one here. With ice. Okay. Where is Zoom? Where is share? Share screen. What am I sharing? Let me see. Okay. I'm sure you guys can see. This is the first one I'm going to actually look at. The first work that was actually sent to me. So, first and foremost, okay. So let me see. Okay, this is one person who sent the work. So, just as usual, what happens is that you normally get the denominator and you're going to use it to actually find your values of x, just as the person here did. They used it to find the value of x. So here they used this. I don't know whether you guys can see. Okay, so here what they actually did is they used the formula, which is this formula here. X is equals to negative b plus or minus square root of b squared minus 4ac over 2a. So there, from the equation there, which is x squared minus x minus 2 is not equals to 0. It shouldn't be equals to 0, because if it's equals to 0, that means your entire thing is going to be wrong in that situation here. It shouldn't be equals to 0. So what happened is here, the person found the values of x. So the first value of x that was found was 2, which is actually correct. The second value is supposed to be 1. Yeah, second value is supposed to be 1. And then from here, the only thing that's missing in this case here is a table. We have to draw the table. The table is essential. So here, the table was supposed to be drawn. Yes, yeah. So you found your value of x and you found your value of y. So you found your two values of x, x1 and x2. x1 is 2, x2 is 1. Thank you. x2 is 1. It's supposed to be 1. Yeah, 1, 1, 1, 1, 1. Yeah. And then from there, what happens is that since here you found your two values of x and two values of y, remember that in this case here, it's a fraction. Like you're looking at a fraction of two quadratic functions, I should say. Yes, so what you're going to do is just like the other one, you also have to, so you're also going to have to incorporate even the other equation as well, like the other equation, yeah, in this case here, for you to actually find the domain function, because you can't just end on the first one, because you've only applied only one part of what do you call this? Only one part of the question, which is the bottom equation you've been given there. So there, that's how it's incomplete. But I really like how you started. You know, it's okay and everything else. Yes, yeah. And then like since you also have to introduce your other one, yeah. Just the other one there is supposed to make sure it's supposed to write like we did the other one where it was greater than 0, and then from there we now solved for that. This is why it's important for you to actually draw the table and everything else and all that. Yeah. Yes, yeah. But anyway, I will solve the questions myself. And then for the other one, this one here. But then this one here, the signing thing was very correct. Only a few things are actually left. You didn't finish writing. How did you come up with this? You haven't shown us this part. You only solved for one part. The other part is left. The part that's left is for this. Is when you incorporate both of them and when you say it's greater than 0. So that's the only part that's missing in this case here. But the beginning you said very, very well. That's very good. You found your x1 and x2 very, very good. But then this, it's incomplete. Yeah. And we are going to actually solve, and yeah. And then for this one here, we're given gx is equals to sine the power 3x cos x to the power 3 over tan 2x. So for that one, there already what you've been given is you've been given sine, cos, and tan. So as usual, you get your bottom part. You're going to make sure you say, just as he did here, it's not equal, so he or she did, it's not equals to 0. as usual, that we already know. And then from there, what you're actually going to do is, because in this case here, this is now a different scenario, because now you've been given sine, cos, and tan is different when you've just been given any random equation and all that. So in this case here, you've been given sine, cos, and tan. I know with these sine, cos, and tan, at times you have to introduce pi, k, and everything. So I'm sure you guys have already done like that circle. Yeah, that circle, that's there in algebra, where you have your sine, your cos, and everything else. What this means, pi over 2 negative. I don't know what's that. I can't remember, and all those things. Yes, yeah. So yeah, I like how you started and everything else, but just somewhere a little bit. It's not complete and all that. But anyway, I will actually solve it myself. I will actually solve it so I should show you guys how to go about it. But otherwise, I really like the solving and everything else. Yeah. So let me go to the next person. Okay. Let me go to the next person. Just hold on. Give me a second. So I've seen this one. Oh, this having it loaded. Okay, they have. I want to see someone who did the limits. I want to see the limits. I'm only going to look at one. Like, I've already looked at one for the, what do you call this? I've already looked at one for, no, not this one. I need someone who did the limits. Limits. Wait, someone did the limits. I was going to limits before the class started. Okay, yes, yeah, okay, all right. Okay, just hold on. Okay, so okay, so I'm going to look at this work. Yeah, so the limits. So the limits that I gave you guys, the first limit I gave you guys was that one there. Limit x approaching 0, sine 3x over sine 4x. Yes, yeah. So what happens, is, as Kasonde had actually solved, she replaced the x as usual. You replace the x with the 0, and you find 0 over 0, which is very much okay. And then from there, she explained and said it's form indeterminate, which is very correct. I like that. Yeah. I even like the fact that you even explained, like you said, which is very, very good. Yeah. And then from there, she now simplified. Yes. So now, like, initially, how you simplify under limits is that just as she started, she said you first replacing your limit inside the equations, the fraction that were given. Yeah. And then, because there are times like when you replace with whatever it is you've been given, you actually find there's an answer, and you have to further like solve it and everything else and all that. No, you have just directly and everything else. Yeah. So she did that, the first part there, and then the second part, it was supposed to remain sine. She have stayed sine 3x over sine 4x there. Yes, yeah, should have just stayed just like that. Yeah, I'm sure if it stayed, yeah. But otherwise, I will solve it. But I actually just like the way you solved it. It's very, very good. Solved it very well. Yeah. But I'm just going. There's somewhere where you made a mistake. I think if you left the sign, and didn't put the cos there, you'd have found the correct answer. But otherwise, it's very, very good. The next question we're given is this one here is square root 1 plus x squared minus x. The limit in this case here is negative infinity, isn't it? Yeah. So what happens is, for this question here, how we solve these questions is that in this case here, even when you replace like everything, all the values with infinity, you still have to like further just solve the question in the first place. So yeah, you still have to solve the questions further with the actual solution and everything else. Yes, yeah. So okay, let me just let me solve the questions. Otherwise, I like how you guys are actually solving the questions. Very, very good. That there's just a few things that need to be clarified. Otherwise, it's very much okay. Yeah, you guys are doing well. Yeah. Let's see. Where is the first question? Just hold on. I'm going to show you guys. Let me see. Where is the paper? I wrote on. Okay. We'll start with the limits first. Ish. I'm not getting it. So. The first thing I'll start with correcting is the limit. I'm going to correct one. I'm going to correct one of the domain functions in one of the limits. Then the other ones, I'll just send you guys a correction, but it's the same application. Yeah. So the first limit. Which limit do you guys want me to explain between? You guys should choose between the questions I gave you. Choose one from the domain functions and one from the limits. The one you guys should think. The ones you guys think I should explain. I'm waiting for you guys to choose. Yeah.
The last limit.
The last limit.
No, I think
Okay.
the first.
You think the first limit?
The last one.
Last one. Okay. Okay. Someone says, okay, the last one. What's the last limit? 2x plus 1e the power negative half. Okay. All right. That limit is actually very, very simple, you know? It's very simple and very direct. Yeah. Okay, so the last limit was get out. Okay. The last limit was limit x approaching 0, 2x everything 1 plus e the power negative half x. So what happens here is that this one here is going to be very direct. So as usual, where there is x replaced with 0 over here 1. When you're going to replace 0 here, the whole thing here is going to give us 0 actually. So it becomes 1 plus 0. Yeah. And then from there, you're going to have 0 over 1, which will give you 0. This is how you solve the first one. This is your answer. Since it's short, I'll solve the other. I'll solve which other one did I solve? Someone said the first one. So the first one. Huh? Everything over. Sorry, over sine. Where's my Tipex? Okay. Sine 4x. So I'll solve the first one, sorry, the last one, and now I'm going to solve this other one here. So what happens is, for this one here, one of the easiest ways to solve it, just as Katunde had solved it, the first thing you're actually going to do is you will just say sine, where there is x, you're going to put 0, and then sine, where there is x, you're going to put 0, and then from here, the answer you actually find is going to be 0 over 0, and this here is not correct. You cannot end here in 0 over 0, you can't end here. Here is different. It's different how, because here was 0 over 1, why we ended here was because here it's actually okay. It would have been wrong to end here if it was 1 over 0, but in this case here, this is actually also very, very much okay. So it's okay the way it is like that there. Yes, yeah. So that's what you. I have to just confirm something. Just hold on. Where is my calculator? Okay, thank you. Just hold on. Give me a second, guys. I'm coming. Where is that? I just need to confirm something really, really fast. Let me see. Sorry, I was just trying to confirm this part here because I know that exponential to the power 0 is equals to 1. It's not 0. So here it's going to be 1 plus 1 to give us 2, and the answer will still be 0. Yeah. Remember, exponential to the power x, so exponential to the power 0 is going to give you 1. That's how it is. Yeah. So here the answer is here. The concept of where you just replace directly and everything else, it's actually very much correct, because in this case here, our solving is actually very much okay, because here our 0 is on top, so still at the bottom, and it's very solvable in the case that we know we're able to solve this part there. We found 1 plus 1, we found the 0 there and everything else. So here, this concept here is very much okay. You end here, this is your final answer. Yeah, this here is your final answer. Yes, yeah. Now for this one here, what happens is, since we found 0 over 0, and then we can't end on 0 over 0, so we now have to find a way to solve it, or rather to simplify what we've been given, and then replace, and then actually now be able to, solve and everything else. So one of the first things, how an easy way of doing it is, the first thing I'm going to do is we're going to get our, so we're going to get our sine. We're going to get sine 3x over sine 4x. Yeah. And then from here, what's going to happen is that we are going to say times 4x. Yeah, times 4x everything over sine 4x, like that there. Yeah, everything over sine 4x, then we'll say times what we've been given here, like what is actually here, going to be 3x over 4x. Yeah, 3x over 4x. This is just an easy way of solving the question. Why? In the case that, why in this case here, when you solve it like this, you're just trying to simplify the work, so you can actually like have something to cancel and everything else and all that. Yeah. So this is how you're going to do it here. And then once you do it like this, and then you just do a few other calculations and all that, you have to just simplify it from where it is here, that there. Yeah.
Mono,
Yes.
how did you come up with the values on the other side? Like, why did we get 4x over sine 4x?
Oh, because like when you look at our sine x, the first sine x there is sine 3x, other one is sine 4x. So what we did is it's like we get this fraction, and we say no, let's break it down. Yeah, let's break it down in an easier form, or an easier form. Yes. So what you do is that the first thing is you're going to detach. First of all, maintain your sign and maintain what you've been, maintain your question. You maintain your question. Then the second thing you do is you detach what you've been given. Our 3x is there, our 4x is there, right? The next thing we have, actually, this step is necessary in the case that it will help you simplify what it is that you've been given. Actually, it's supposed to be like this. Sorry.
Mono.
Yes.
So you mean whatever, when all these things are multiplied, we simplify it, will take us back to where we started from?
No, it won't take us back to where we started from. Just hold on, chill. I'm doing this so that it can be simplified. Sorry, just hold on. Give me a second. Let me just correct this. Okay, that there, that there, that there, that there. Okay, there. So what we're doing here is that one way is just for us to break down whatever it is you've been given so that you can actually find the answer. So the first thing is you have your sine 3x, your sine 4x. First thing, maintain your sine 3x and maintain your sine 4x, like that there. Second thing is that we now get our what we've been given, like what's in brackets, your 3x over 4x. You have your 3x here over your 4x there that we already have. Now we have to now find the way for us to, we have to now find the way or find what we're going to put like in the middle, so that when we simplify it, it should, like everything should be cancelled, or rather it should just be simplified. Because no matter how much you try to solve this, we'll still be finding 0 over 0, and the answer cannot be 0 over 0. So we said no, let's use this method so that we can now find the way, to simplify the way. So what we did is maintain whatever it is you've been given. The second thing we did is get what was in the brackets, which is 3x over 4x. The next thing is you have your middle section in this case here. What do? You just change other positions of what you've been given. Yeah, this is much easier than the one I did at the beginning. I would have had to explain other things, but this here is much easier. Yeah. So from there, what are you going to do? The first thing is sine there, sine. These things are the same. They'll cancel. Here they'll cancel. What are you left with there? Then the x and the x are also going to cancel. What are going to be left with there is actually going to give us 1 times 3 over your 4 there, like that, eh? And then from there you'll find answer is actually going to become 3 over 4, which is your answer for this limit here that you have been given him. This is just one of the ways that, like, when you try to use all the other methods to try and solve the answer, and then you can't, then you're still finding maybe 0 over 0, infinity over what, infinity over infinity, and everything else. Yeah, you can just find another method for you to simplify the work, so that you can just find the final answer. And this is one of the methods that's there. Yeah, it's not common, but it is there, and it is used in the case that everything that you have solved, I don't know, is like it's just giving you maybe 0 over 0 and everything else. Because in this case here, if we tried other methods, we're still going to get 0 over 0, or maybe we're still going to get some other factor or other thing. So in this case here, we use this method here so that we can just simplify the work much easier, much faster. And then you guys have even seen how the x values here have, so the variables have been cancelled, and because it's the variables that are causing the 0 over 0. And once you cancel the variables, it makes the work much easier, because what are you left with there? You're now left with the coefficient 3 and the other one, which is going to be 4, and therefore the answer is actually 3 over 4. That's how it is. That's how I found this answer right here. So this is for the first limit. I also solve the third limit.
Wait,
Yeah.
Mono.
Yeah.
I have a question on the same one. Usually when there's that one, like 0 over 0, as it's indeterminate, something like that, isn't it that you can also use L'Hopital's rule? So is it you can use L'Hopital's rule, right, to solve?
Yes.
I'm kind of asking if you could use L'Hopital's rule in the, to solve, and to see if we'll come up with the 3 over 4.
3 over 4? Okay.
Yes.
Okay, I'll use it. Let me solve the other question first, and I'll get back to that question, okay? Okay, so let me solve this third one so I can do the other one using the other method. So we have limit x is approaching infinity, and then square root 1 plus x squared minus x. So just as usual, the first thing you have to do is you replace where there's x with infinity. So you're going to say square root 1 plus infinity square minus infinity. When you solve here, you get infinity over infinity. And then this here are going to say yes, yeah. So from here, what we're going to do is we're going to use another method where what's the method called? Okay, I'll put in the method what's called this, yeah. But I'm sure as you guys as I solve, you guys will see the method I'm using. Yeah, the name has just gone. Very sad. Anyway, limit x is approaching infinity. So we have square root 1 plus x squared minus x, right? So from here, what happens is that we are going to find the opposite of this here. So we'll say square root 1 minus, so it's 1 plus, yeah, it's plus x squared minus x, right? Put this in brackets. What's the opposite of this? We're going to say square root of 1 minus, sorry, not 1 plus x squared, right? Here it will be plus x, like that there. Everything here will be over our opposite that we had, over our opposite that we already have here, which is this one here. It will be square root 1 plus x squared plus x there. So this right here is what we're going to use. Then what happens here is that when you use the opposite of what you actually have, what you like, this part here is already simplified. What happens here is that the square roots, they are going to cancel, and then from there the sign there will remain here. The square roots here will cancel, this and this, the square roots will cancel, yeah, that will become negative. Yeah, so it will cancel like that. You have 1 plus x squared, this and this, like the signs, yeah, it's going to be, you look at the signs, when you try to multiply those signs there like that, or rather simplify the signs, you still, the final sign you're going to stay with is actually going to be negative, yeah, negative x, yeah, negative x. Since remember you're multiplying these two, negative x squared, everything over what, sorry, I didn't say my battery was low. Anyway, yeah, so this is our actual equation, yeah? So we bring it down here. We find the opposite of the actual equation, which is going to be square root 1 plus x. Everything over the opposite, square root 1 plus x. Our initial question was minus x. Now we're going to use plus x. So after we've now written our equation like this, the next thing you have to do is this top part here this top part here can actually be simplified. When you multiply this and this, what do you get? The only thing that changes here is that your square roots are going to cancel, and then you just keep what's inside. That's one of just the easiest ways of just simplifying this, because if you want, you can always distribute that and further multiply, but then that's just a whole other longer method. But I'm sure you guys remember this in math, that when you have such a thing like this, the square roots are going to the square root to cancel. You only keep what's inside. That's 1 plus x squared, and then from there, what's outside, in this case, you multiply this. Then what do you have? Negative x squared, which we have here. The bottom part, you're going to keep you keep the same value that you have there, which is square root 1 plus x squared plus x in this case here. Then now when you now reach this point, we are now going to try and replace with infinity in this case here, and then now see if we can find a value. Then if you won't find a value, we'll have to now further try and simplify the way until you can actually find a value. Yes, yeah. So what's going to happen? Yeah, so what's going to happen here in this case here is that, since you can see now here, what's common here is x. Yeah, what's this one is the smallest number is just x alone. So if we want, we can always just use, like, remove the x. Yeah, just remove the x. Always remove the x. Always remove the x if we want to. Or what we can actually, the other thing we can do is that we can say 1 plus x squared minus x squared, everything over. If we try to just get rid of that, what we're actually going to have is going to be 1 to the power half plus x2, yeah, plus x2, this is squared, plus x2 times 1 over 2 plus x there, like that. Then yeah, let me see, this and this they can actually cancel, and then they'll actually remain with 2x there. Then okay, let's see, this will work. 1 plus x squared minus x squared there will still remain with 1 to the power half. Just hold on, let me see something. 1, where is that? 1 it's a fraction. Okay, yes, yeah. So what's going to happen is we simply, like, we've just tried to simplify this so we can actually try and find an answer. Then there is going to give us 1 there. The whole, like, the x was squared, but like the general power is actually going to be half, and then that in that, like, the powers are going to cancel there. The 2 cancel the half. Then from there you have x plus x there. Then you have 1 plus x squared minus x squared, everything over 1 plus 2x there. Let me see. And then from there, let me see. And then from there, let's see if we can say x squared there. If we try and get rid of the x, because here we will still have infinity over infinity, and it can't be infinity over infinity. So now to find the way to simplify that. So what we can actually do is, in this case here, we're going to remove the x. We remove the x here, so we'll have x there. Then we'll have 1 over x plus x minus x there, like that there, isn't it? We'll say over.
But Mono, can you position your phone?
Oh, sorry. Okay, do it like that there, and then from there move the x, remove this other x here. We say x over 1 plus 1 over x plus 2. That in that day is going to cancel. Let's see if we're actually going to have a value there. So we're going to have our whole number there is 2. Here we have infinity over here we have infinity. Here we're going to have infinity there again. But here infinity over 1 is going to give us infinity over 1 is going to give us, so here we're going to have a 0 there, like that there. 0 plus infinity will still give us infinity, and here we'll still have infinity. So let us try again to get rid of another x as well. So let's see, we flip the other side. What we're given, what we are left with, just you, is 1 over x. Let me just write it down quickly. Hold on. 1 over x plus x, 1 over x plus x minus x, everything over 1 over x, everything over 1 over x plus, which is the whole number, isn't it? Yeah. Okay. So we're left with this. This is what we're left with. And if we try to actually put our limit here is infinity, we'll still get infinity over infinity. Here it's going to give us 0, but here we'll have infinity. That's the only problem. So it's still, let us try to again like just simplify it once again. Yeah, so from there, let's say we get our x. Get x there. What we are actually going to have again is going to be 1 over x. This part here, 1 over x, again we'll have to say times 1 over x actually divided by x. Just hold on. Yeah, 1 over x. Let's see, 1 over x divided by x, like that there, 1 over x, the x, yeah, it will give us 1. It will give us 1 there on top there. Sorry, just hold on. Okay, there, and then here we're just going to have plus 1 minus 1. Here it's going to, here we're actually going, this part here, once we move the x here, we remain with 1. Here, well, here we're actually going to have 0. here actually going to have 0, and then here we're going to have 0 and everything else. And then from here, let's see if we get rid of the x. Let's see if we get rid of the x like that. There, here there's no x whole number, but there's an x fraction. But we can get rid of an x fraction. Sure. Let's try this. Okay. Just hold on. Let me try to get rid of the 1 over x. But the answer I'm supposed to find here is 0. Yeah. The answer I'm supposed to find here is 0. Yeah. Get rid of the 1 over x. We're going to have 1 there. Have this 1 whole number plus x. Yeah, this 1 whole number plus x over oh yeah, x over 1 over x. Yeah, and then minus x over 1 over x, like that. There, everything's going to be over 1 over x, open bracket 1 plus 2 over x. There, this part here will give us 0. Okay, this part, this part will swap like that. The x, let's see, this and that, this and that there will cancel there, like that. There, that and that, see, this there will cancel like that. There, this part here going to give us 0, that there will come out there to give us 1 there, and there 1 over that there, like that. Our initial thing we actually found is supposed to be 1. Okay, all right. No, anyway, let's just do this trick. So we'll go back the beginning so I don't continue solving, otherwise we keep on solving. Yes. So what happens here is that once we simplify this whole thing, right? So one of the things is this part here, the same thing here and here will cancel. We'll have 1 over square root 1 plus x squared plus x there, like that there. And then from there, what we have here, we replace the infinity, that become 1 over infinity, which is actually going to give us 0. And our answer is 0. Yeah. Yeah. So let me see. Forget this part. Just this part there. Yeah. So this limit here, we did that there, found this there, and then from there we use the opposite of what we've been given, which was plus x, plus the same plus x at the bottom there. We simplified that. What we got was 1 plus x squared minus x squared. This and this here simplify, we get 1 at the bottom. This part here cannot be simplified. Once we now once we replace here, have
No.
yes.
Can you please take us through the multiplication? I'm lost somewhere. Just there on top when you're multiplying them. Right here. Yeah, like
Yeah.
how exactly were you multiplying and how we came to this down here?
I got this down here. Okay. So the first thing is to multiply what's been square rooted. And when you multiply two fractions or two numbers of the same value after two fractions, and they have the same things inside the fraction, and they have both been square rooted, what you get is what's inside. That's one of the things is there.
Yeah.
Under limits.
But won't it be that from there now we'll multiply that with the x at the end?
No, because look at what happens is that this part here and this part here, this part here and this part here is one thing. Yeah, this part here and this part here is one thing. Quite all right. Yes, yeah, you can multiply like that. But then the thing is that normally, let's say for example you've been given x plus you say x plus 2, and then here you've been given x plus 3. How would you solve this? You would distribute it like that, right? You would do this, right? The same thing applies here. Yes, yeah, the same thing will apply here. You would get this, multiply with that, this, multiply with that, this negative x there, this like that there. Now, one of the secrets that's there is that when you're multiplying two square roots of the same value inside, what you get is the value inside. Just like when we say square root of 2 times square root of 2, your answer is 2. Square root of 3 times square root of 2, your answer is 3. Yeah. So that's actually how we got the 1 plus x squared, right? And now for the other part is now, what's next is now this part here. This part here is negative x here. The other one here is positive x, isn't it? So multiply this times this x times x will give you x squared. The sign negative times positive will give you negative. That's how we found this one here, like that there. Yeah.
So is it that for limits we just multiply the first one and the first one, we don't go to the next one like they were supposed to do for those the example you gave on the side?
Which one?
Because if we are to do the same thing, can you just position the camera?
Okay. Mm-hmm.
Yeah. Let me see. Can you take it a bit higher? I can't see the other part. Yeah.
Mm-hmm.
The first thing you did was you said square root of 1 plus x squared multiplied by square root of 1 plus x squared, which gave us what is just inside. Then what if we now do square root of 1 plus x squared times the x which is at the end? That's the value I was not seeing. So I wanted to get clarity there.
Oh, okay. No, you can always do that if you want to. You can always do that, but then that's a way longer process, because now they now have to multiply that and then simplify until you find the actual value. But then one of the easiest methods or easiest ways to actually solve this, like when you've been given such a question, is multiply. Yeah, multiply what is square rooted. Afterwards, they multiply, and then you now multiply your other things which are left. It's just one way that just makes the things faster and easier. It's like a trick, but if you want, you can always go through that whole thing of where you say 1 square root of 1 plus x times the same thing and then times x, and the other is negative x. You can always do that. Yeah, but at the end of the day, you still come back, it's 1 plus x squared minus x squared. You still find that same value. Yeah.
Oh, okay.
Mono, can I say something?
Yeah.
Okay, to make it a bit simpler, can we just say, since we're using the opposite, which is more like the conjugate, can we just say it's a difference of 2 squares? So we'll say the square root of 1 plus x squared, brackets, everything to the power 2, then minus x to the power 2. Then the square root to cancel with the power 2 and we'll have, no, chill. Wait, let me see. Yes, since it's the opposite, we'll say a difference of 2 squares. So we'll say 1 plus x squared, I think, minus x, everything to the power 2. Then we simplify them. Yeah.
Yeah,
I'm not saying the right thing. Oh, yes.
Yeah.
So which means we'll say square root of 1 plus x squared, everything to the power 2, minus x squared. So this the power 2 will cancel with the square root. We'll have 1 plus x squared minus x squared. Yeah, like it will come up to the same, rather than multiplying, trying to open the brackets. Can we just use the logic there?
Yeah,
I don't know if it's better.
Yeah. At the end
Okay.
of the day, at the end of the day, thank you. At the end of the day, you have to find what is easier for you. And like just as she said, she's found another way to like actually find the answer. Yeah, which is actually very nice. Yeah, so that's how we found that the answer was 0. Yes, yeah. Yeah. So let's see what's next. Okay, so I still have okay, that was the first question. I have to use the other method, but before I do that, let's at least just start with what you call that. We do the other example I had given, the other work I had given under the domain function.
Wait, how many methods do we have altogether?
There is fraction. Wait, there's what's it called? Guys, I'm so sorry. I've forgotten
It's
the term.
rationalization.
Yes, there's that one.
Rationalization, yeah.
There's that one. There's what's there? Oh yes, yeah. This is conjugate. Yeah, that one from doing here is conjugate. Then there's the other one. What's the other one? Catherine, there you had said it. What's
L'Hopital's rule.
Yes, yeah, there's that one there. That's the common one actually. That's there. Actually, there's the other topic we're doing. Is going to have a lot of that one. Yeah, those are the main three that I actually use. Guys, there's also first principles, except it's not used. Oh, you can actually use first principles to solve the one we're from doing instead of using conjugate actually. But it's just too long and very unnecessary. What you do is whenever you're solving limits, let's say if you can use all three methods to actually find what you're finding. Normally what happens is if you're using one, you can't use the other one. That's normally how the suits are. Because let's say for example, you can't use conjugate for all of them. That's just a fact. You can't use conjugate for all of them, and the other one you can't use it. You can only use the other one too when you have when they are similar. So what happens normally is that you find something or find the process or find the method that is way faster. Because normally, let's say for example, how in this case here we use conjugate. We use the opposite of what we've been given, which is conjugate. We use conjugate. Then you can use conjugate, or the other one is you can actually use first principles. And first principles is way longer, but then it does work, but it's way longer. So what you do is normally is that when you're solving limits, try by all means to find a process that's very, very fast and will still give you the answer. Because the whole process or the whole essence of limit is for you to actually find the answer. Unless your question has been specified with what way they want to use, what method they want to use. If they say no, use development limit, then you will say, okay, no, I'm going to use that method. I have to use that. Under that one, what happens is they give you what this is equals to and everything else. So that is actually very, very simple and very, very fast. So it's a matter, and then it's a matter of what you've been given, and you try by all means to find something that's very fast and will help you find the answer quickly, so that you don't waste time. So you don't waste time solving questions, solving. No, just find something that's very fast and very rapid that will actually give you the answer. Like the one that, like the question that I was from solving. You see how long I was solving and everything else. When the simplest thing I would have done is just simplify that part there, get the one, simplify that part there, you get the one on top there. From the one there, you replace at the bottom there and find the answer, and it was 0. And me going through all the steps. So you see, all that time that was wasted there, I would have just simplified that part there. The same thing, the same thing. That's why it's very important for you to at least be familiar with all the methods, but then just pick one that at least is easier for you, and still, yet it's easy, yes, but still it should also be very, very effective and very fast as well. So you don't waste time. In the limits, because limits are questions where you have to get them correct. Because limits are very simple, you get them correct. Once you solve a lot of limits, you'll find it'll be very, very easy. Nonetheless, if they even tell you that no, I use development limit, that one is very, very easy. Unless maybe they just change something and everything else. So just try by all means solve so many limits and everything else. I still have to solve the other limit as well. I'll still solve that one. Yes, Before I solve it, let me at least do one question under the domain function. Yes, so at least even though we don't finish,
that means at all times there will be one formula to give us the correct answer.
Oh yes, there we go.
Okay. Then in an instance where you're solving a question, then maybe you try out a method and it's wrong. How exactly do you present your work, since you've been told you have to explain to the professor as you are solving? How exactly do you do it then?
Okay, so what happens is, let me show you an example in my book. Let me see if there was one where I had to explain. Just show. What is that? Okay, so I'll give an example of this question here. Who is it? No, not this one. Okay, I'll give an example of this suite here. That's the work here that they had. Yeah, I'll give an example of this suite here. I know all of you guys can see of this suite here. So what happens is that in this case here, the only thing is I was just like here. The thing is I was just supposed to solve the suite. Yes, yeah. Oh yeah. No, let's look at this one here. I actually had to calculate. So, like for this one here, you've seen it. The only thing I had to do is just to solve the suite. That was the thing. Just solve the suite. That's all. Yes, yeah. So, like, you have to use words like swap, use don't, use swag again. Like, let's say for example, like the way I began here. This is like how an example of you explaining to the professor, like each step, So I said right here, I said by saying SWA, f of x equals to x squared is equals to square root x plus 2. I wrote there. I said x is a member of the f. I wrote there. The main function there. I wrote it there. I came down there. I came down there. I differentiated what was in here. I differentiated like what was in the square root there, x plus 2. So the square root of x plus 2, I differentiated that there. I found the answer there. I found the answer there. I even found my interval there. And then from there, I know how to explain this interval. How do you explain this interval? This is how I explain the interval. I wrote it like this there, and then as usual, remember what I told you guys last time. F is always a constant, guys. That's how there. I said no, f is a constant. I had to introduce the L. I introduced the L as usual. Of the limit un. Yes, yeah. As usual, n was going to be approaching infinity. And then from there, I had to explain a little bit there. I solved the question there. After solving the question, after continuing solving there, I came here. I still had to write this and write. I wrote, you see, so that what happens is that normally, like explaining it to the professor. Normally, you explain to the professor when you are looking at suites. Suites is where there's a lot of explaining, because you have to like tell them like what step, like what this means, because under suites you'll be using so many signs. You're going to introduce the L. They have to know why is there L, why is there the F, what is the F in the first place. Yeah, that's why it's important. Yeah, that's why it's important for you to actually read through the notes, like under suites. Like in suites, notes are actually very, very important. Are very, very important. It's unlike when you're looking at limits and other things, like most of the times, like you don't really dwell on like the notes, but under suites, you need to actually read the notes and go through the notes. This is how you explain. You have to explain, no, this and this. No, why, what is the L? Why did just the L? This, normally under limits, you can only use, maybe the only part where you explain is maybe 0/0 and such things, then you would explain. Otherwise, you don't really have to explain like under limits a lot. You explain so much under suites. Yeah. Yeah. Hope I've answered your question. The person who asked about explaining. Yeah, under limits, you don't have to.
Yeah, it's very clear.
Only much to explain. I said I was going to solve the domain function. Let me see. I said I would solve at least one, so that let's see. I'll solve. Yes.
We can't see it. Just dark. I don't know if it's just me, but.
Oh no, don't worry. No, don't worry. It's not just you. I've just dropped the phone. Just hold on. I'm trying.
Okay.
Yeah, I'm trying to see which one of Of the three, I'm going to solve. I want to solve the one that's a little bit more complicated.
All right.
I won't solve that one, no. This one, ln 1 plus x, no, that one is very simple. Let's see. Okay. All right, so I'll solve the same one. Okay, so then I'm going to be solving. I'll solve the first question, and yeah, I'll solve the first question under what do you call this? Under domain function or intervals. So it was gx is equals to square root x squared plus x plus 2 everything over square root what's behind? Okay, everything over square root over x squared minus x minus 2. There, like that there. So the first thing here, we're going to do is that in this case here, for this one here, this question here is a little bit different from the other one that we had looked at. In the case that in this case here, it's not like the one where it was like ln of ln of the whole thing. Like, okay, you see this one here, what happens is that you have this fraction here is on its own, and this fraction is on its own, right? The one that was the ln in this here was for the entire fraction here. It was like the whole thing here, this whole thing here, and this whole thing here. The ln was for 2x 2 minus x over 2 plus x. You see, this and this, very different, two very, very different questions. Yes, yeah. So the first thing we do is, so in this case here, because now this is different from the other one that we had done, so just as usual, we have to find the value of x1 and x2, which we already found. I won't have to calculate that. Already found the value of x1 was equals to 2, x2 was equals to -1. So we found these two values. Yeah, we found these two values. You guys already know how to solve how to solve these two values, how to find these two values, eh? Yes, yeah. So we found that one there. So we found that there.
Anything about December. I just said being good. And then when it's all and that I'll just people line like December, I open like a sleeping emoji. What am I supposed to say about that?
Chisembo, turn off your mic.
Oh my goodness.
Yeah.
Yeah. So so in this case here, you have got two different equations there. So you have to find, okay, so how to find the value of the x and x1, the x and the x1. So we found this here, but let's just do this. Okay. So the first thing I'm going to say is, hey guys, I need space. Then this table also is for begging. Okay. So as usual, how do we start? We know how we start. We always start by saying x is a member of the f, isn't it? Of the f, that we already know. We put the equivalent sign like that there, a. So once our first fraction we have, only get what's inside. X squared plus x plus 2, right? As usual. Because in this case here, it's different. It's different. It's not like the other question. It's a different scenario. Why? Because here you're looking at two different equations. They're separate equations. The other one down for ln there, the 2x, the 2 minus x over 2 plus x, that was a whole thing together. Indeed, it would have been similar to that question there if we had like the whole thing here was ln, but it's different. Here, looking at two individual equations here. So have that there. The first one, as usual, we'll say greater or equals to 0. Why? Because this one here can be equals to 0, it's okay. But this one cannot be. It cannot. It cannot. It just has to be like that. It just cannot. It just can't. Yeah. So we have that's going to be greater or equals to 0. And here you put and. Put your and there. Then we'll say x squared minus x minus 2. This one here is just going to be greater than 0. It won't be equals to, because once it's equals to 0, the whole goddamn thing just becomes wrong. It can't be, it's not going to be okay. Yeah, we really know that something cannot be over 0, but it can be, like, can be 0 over something, but not something over 0. That's, we all know that. So we have these two. As usual, we have to find the values of x for the both of them here, for both sides. And for the first one, for the one where the charge is negative, for this one here, x1 is equals to 2, x2 is equals to negative 1. We already found that. Yes, we already found that, isn't it? Yes, yeah. And then for the other one, I think we'll find the same thing, isn't it? Let me see. Not that, okay, there's a possibility of finding the same thing, but yeah, we might actually find the same thing. Sure, hold on, let me just see. Okay, yeah. So we'll find that there. We found x1 as 2 and x2 as negative 1. So in this case, remember, you have to draw the table here. Now for here, what happens is that in this case here, we'll just have a simple table. It won't be like the other one. So what we'll do is, since here the equation we have used to find the value of x is the one with the negative sign. So okay, so what we're going to actually do is that, let me see, we'll just end this here like that there, and then here we're going to actually write x squared minus x, because we've used a negative one. We've used the denominator to find the value of x, x1 and x2. We use that one. We maintain that simple rule of using the one at the bottom to find the x1 and the x2. So we have x1 there, like that there. We just put the x here as usual. The values we have, we've got negative infinity, as usual, negative 1. You have your 2, have your positive infinity. What do you do? What are you going to do? As usual, what you're gonna do here is you have to find, you place in each of them so you can find the sign here, the sign here, the sign here, and the sign here. Yes, that's what you're actually going to do in this case here. So if there I put negative here, let me see, here it will be negative infinity, here it becomes plus, here becomes plus. What's dominating there is actually going to be, let me see, hold on. Oh, no, it's squared, eh? Yeah, so here it's squared. So because it's squared here, the sign, everything here is going to be positive there. Let me see this. Let me see here. The same thing, yeah. The same thing when we solve for negative 1, also be positive there. If you put 2 there, here it will be negative. Here, if you put 2 there, it's going to be negative actually there. And then here, let me see, and then here we have square root, we have infinity, we have positive there as usual, and then we have this times this, no, this times this. Let's see. So if we say negative infinity times 2, we're going here, what we're going to actually have is, we have positive there, and then here everything has already been square rooted. So our charge here as well, rather our charge here is also going to be positive there. Okay, so what we're going to do is find the value of x and y. We use the bottom value to find the value of x and y. And because of that, that same bottom equation is what we're going to use to find what's in our box, to find what it is, our signs, because our signs are important. There are times when you use the signs to find your intervals, and there are times when you won't need them to find your intervals here. But it's just important or wise of you to actually use your draw a table. So what you do is, what are we using? The x squared. I'm about to explain how I'm finding the signs, don't worry. So what we use is the x squared minus x minus 2. minus 2. Oh, and why do we find the signs? We are doing this so that there are times when you need what you find. There are times when you need what you find, when you need the signs to help you determine how your interval is going to be. And there are times when a question or rather what you find will be so direct, you won't need to actually use your table to help you find the interval. Then there are times when it's used, there are times when it's not used, but we just at times actually use the table to actually find what it is, use the table to find the sign, which will help us with the interval, will help us with whether our brackets will be open, closed, and everything else and all that. Yes, yeah. So in this case here, we've been given this here. This is our denominator here, and what values we have, the ones we found were -2 and so -1 and 2, but then you always need to add your infinity, because in this case here I know infinity here, because first of all what happened here is that our sign when we were solving was just greater than 0. It wasn't equals to 0, so we do not know where it starts and where it ends, so we just leave it open. We leave the option open, so that's why in this case we have to introduce our infinities. So we introduce both our infinities there. You use whatever it is you have there, your infinity, negative infinity, you place it in your equation. In this equation here, you find this sign, -1. You place there, you're gonna find that there. The same thing with the others. So this will actually help you find the values. It will help you find the intervals sometimes. Sometimes it won't help you, but the cases where it's actually going to help you find the intervals. Yeah. And then so from there, you have that. Yeah, you have that. And yeah, we have that from there. Then what we now do is we're now going to come down here. Yeah, we'll now come down here and try to write the equation. So as usual, we have that there, like that there, right? So what's our starting point? Our starting point here is negative infinity. So we're going to say open bracket negative infinity, comma, -1, isn't it? And remember, we're actually doing this for this one here. And remember, everything there is open. So we're going to say to be open there. It will be open there. This and we know the sign for and. We're going to use this sign here like that there. And then from there, our starting point is 2, comma. The other part there, positive infinity. Like that there. So you have your interval there. How do we come up with this interval? This whole table here at least gave us an open box, rather an opportunity for us to see what intervals you can have. So we use this part here and this part here. We found that there. Why are they open? Is because we are considering the denominator. That's why everything here is open, because it's this one right now we are trying to consider. Yes, yeah. And then from there, what happens? Yeah, and then from there, what happens? Yeah, and then from here, what happens? From here, you can actually now say, f x is a member of the f, right? So as usual, the equivalent sign there, over and out, x is going to be a member of real numbers that we already know there. Then we'll say and. Then we'll say x will be a member of open bracket negative infinity, -1 close bracket, and then here we are there, and then from there, then we'll maintain our sign. We'll maintain our sign there. Yeah, we'll maintain our sign there like that there, and then we're also going to say x is also going to be a member of the other one there, which is +2, comma, positive infinity, like that there. Yeah. And then now this whole part here can actually be simplified by saying x is a member of, you say negative infinity, -1 there, you maintain this there, you say 2, comma, positive infinity, like that there. Yeah, going to maintain this like that there, And then you now conclude and say, therefore your DDF is going to be equals to negative infinity, negative 1 there, like that there. Then you have your U, which is 2, comma, positive infinity, like that there. And this here becomes your domain function. Let me see. Let me just move. Okay. So, yeah. So, what happens is after we found our signs that we did the table as usual, like another such a thing, find your table. We found our table there. So, the only equation here we're going to consider is your denominator. You already know the value of x1, x2. x1 is 2, x2 is negative 1. And then from there, what happens is that since in this case here, when we consider our this equation here, your x squared minus x minus 2, and because this one here is a denominator, so what happens is that it can't be equal to 0, but it can be greater than 0, which is actually very, very perfect. So what you do is, because of that, it makes everything more broad. It makes everything more broad and more open. That's actually why in this case you had to introduce your infinities. So you introduce your infinities there. And once you do that, so in this case you're like, okay, so we have the infinities, and you also have negative 1 and positive 2. Now let us now try and bring them together. So the first thing we'll bring together is negative infinity and your negative 1. You bring it down together. So you're going to say negative infinity. And guys, both brackets are open. Why? Remember, because in this case here, our equation and is less, so greater than 0, and it makes everything more open. And here we don't know where things are starting and where things are ending. We just don't know that. So we just do it like this. And then from there, what happens is we'll now write the first interval, negative infinity, negative 1. You're going to have this, you're going to use this sign. You know why, you guys know why this is here. Or best breaking things down here. Yeah, because remember, these two, they are together. It's together, they say part of the same thing. They come from one whole tree, which is this equation here. So use that sign there. The interval that's there is 2 and your infinity there. Yeah, and then from there, what happens? You now have to explain f is a member of the f. Therefore, x is a member of real numbers. And then from there, and then you say, and x is a member of the first interval, and x is a member of the second interval that you have there. Then now this second part here can further be simplified by you saying x is a member of the first interval and x is a member of the second interval there. Then from there, you now just conclude by saying your domain function is equals to negative infinity, negative 1, and 2, positive infinity. And in this case here, this is how we found our domain function. This is the method, how we found it. Find the value of your x, find the value of your x1 and your x2. Use the first equation, use the last equation, the bottom equation, dwell on that equation, break it down, find it, draw the table, find the signs, find the signs, look at what is your actual sign, greater equals to, or it has an equivalence. If it has an equivalence, things are more precise. No equivalence, it's a little bit shaky there, and all that, yeah. So that's that there on this equation here, like that's that, yeah, that's that. And then for let me see, for the other one, the one where those ln, it's the same thing like there is of the other one, the same thing, same thing, because in this case here, the only thing that has changed now is that in our first equation there, it was 1, so it was 2 minus x over 2 plus x. The question I gave you was ln of 1 plus x over 1 minus x. The same method, the same method. Yeah, there really isn't any difference with that one there. So that's that. Now before we move to other things, does anyone have a question under what I'm from solving? Under what I am from? Under what? Yeah. Okay, yes. Anyone with the question, please ask your question before I do other things. No questions? Okay. So Yes, yeah. So what's gonna happen is that, let me see.
I have a question.
Uh-huh.
So to find the domain of this same function, you just use the denominator. The numerator shouldn't be taken into consideration.
Yeah, yeah.
Didn't get you.
I said yes, yeah. In this case here, yeah.
Okay, thanks.
Okay, yeah. All right. Okay, so anyone else with the question? Anyone else with the question?
Any question? You mean any question? Or from what we have done?
Yeah.
From what we have done, I wasn't clear on the last question you found. Was it 3/4 or 1/4? The one which had sine
I
3x.
Rose.
Okay, sure. Hold on. Sorry guys, I was eating ice, just forgive me. Yeah, so for that question where there was it was sine 3x over sine 4x. So for that one there, you can use different methods. Yeah, but you can use different methods. So what I did is that for that question there, what happens is, as I was telling you guys earlier on, is that normally under limits you have to find a way to just simplify your work, whatever way it is. Just find a way to simplify your work, so that as you are solving the questions, you don't have to waste much time on, you find this and then you find that, and for it, just take your time solving limits. So what happened is that under that one, I still have to solve it. I have to solve it and use another method. Yeah, I use another method so I should see if I find the same answer. I know I'll find the same answer. Yes, yeah. What I used to find the answer there is, it was like I don't know what method I should call it, but I just simplified it, where I just found the opposite of what I was given and then got what I was given inside, which was 3x and the 4x, made that into a fraction the way it was already a fraction initially, and got rid of the x, because it was the x values the x variables that were giving me the 0/0. Yes, yeah, the 0/0. Yeah. So once I got rid of the x variables there, it made things more open. It made things more open, because they had it made things more close. They had 3/4 in that case there. And then for the sine 3x over sine 4x, I've multiplied it by the opposite, which was a sine 4x over sine 3x. Cancelled that there. What I was left with was 3x over 4x. The x says there cancels. Cancel the x, cancel the x. What are you left with there? 3/x. I used that method there because it was very fast, yet still gives me the correct answer at the end of the day. So I have to solve that question under the other methods, so that I should see under other methods. Yeah. Mm-hmm. Yeah, under other methods. Yes, I didn't solve it under other methods.
That would be better.
Pardon?
Yes, that would be better. That would be better if you solve it using other methods.
Yeah.
Where I was getting lost was, since simplifying and the expansion, they are almost the opposite things, and you had to introduce first the reciprocal of that thing. You multiplied it, which was almost okay, but the last thing you multiplied with it, that was 3x over 4x, which was confusing. I don't know if it could bring us back to the original equation or.
Okay, no, anyway, I see what you're saying. Okay, I see what you're saying. Okay. All right. Yeah, so I'll solve it under other methods and I'll see what I'm going to find. Yeah. Yeah. Yeah, I didn't solve it under other methods. I just used a faster methods to solve the question. Yeah, but I'll solve it using other methods. Yeah, and that will definitely, most definitely. Yeah, I will definitely explain to you guys once I solve it once I solve it using other methods. Yes, yeah. So let me see. Yeah, so we started doing real functions. We did real variables too. So this was basically an introduction to the real functions and real variables. We've actually moved because we've now introduced limits and everything else. Yeah, we have a few theories that we need to do. Yeah, and what else? Let me see. What else we have to do? Yeah, a few theories we have to do, and then my other topic, which is develop more limited, which is actually that one is very, very fast. It won't even take long. That topic is very fast because it's just direct things. It's just full of there's a lot of things that you guys will have to like know and everything else, like know like what this equation is equals to and everything else and a few rules. Yeah, yes, yeah. Otherwise guys are almost done. Yeah, almost done. Yeah, you're almost done. Yeah, I'm sure by the time you guys actually go back to school, you at least have a picture of what is to come and everything else. Yeah, so I won't forget. I'm going to solve that question, and I'll solve that question the same one using, I think I'll try to solve using all three methods. Now, I know I can't solve using all three methods. I think I only use two methods to solve that question. Now see what I'm going to find, so I don't waste time. Yes, I don't waste time. Yeah, the way I wasted time with the other question. Yeah, so then we're going to solve it. So let's do this here. So we should do this. Let's you guys should schedule time before Tuesday. Yeah, before Tuesday, where you guys are free, so that I should explain that question, and so we can finish, at least go halfway through what we have started doing. Yeah. So at least hopefully by next week Friday we are done with Analyse, please. Yeah, so that you guys can just be chilling and just thinking about other things. Yeah, so let's do that. Yeah, I'm going to do that. Yeah, anyway, yeah, so that's that. Let me see, do you guys want to be given more examples? Like, so do you guys want to be given more things to go and solve? You don't have to send me the answers, just try solve on your own. I don't know if you guys want me to give you guys more questions that you can solve on your own and then see if you understood and everything else and all that. Yeah. You tell me. Yeah. Yes, yeah, you tell me if you guys want that. We can always just post in the group, say no more, maybe please send whatever it is and all that. Yes, yeah. Yeah, what else? Yeah, that's that. Yeah, that's that. Yeah. Yeah. So that's that. Let me close my camera.